the later points of time, we can just call the future.result directly. And then it will give you the result if it's ready. So future is pretty simple. It has a status, it has a result, it has an error, I guess. So you can access the results directly. But it's just nicer if you don't do it and you let the IO loop do it, because then you can use the magic yield from syntax that will extract the results out of the future for you.
Does it mean that accessing the result attribute immediately after calling it will block?
No, there will be no result, I guess. You can also check if result is available. So if you want to write a really bad code, you can write a loop in which you would ask, is the result there? No. Is the result there? No. And then you will reinvent the IO loop, because basically that's what it's responsible for. OK. We had this example as far as I know, so let's go further. Demo. I have the IPython notebook for you to show this thing running. Let's agree on the simple case that we are going to test. So we have the client. That will be our IPython notebook. We have a web server. This will be the whatever asynchronous framework we are testing. And then we have 3 APIs. These 3 APIs will be requested in parallel, and so asynchronously. And we want to check how well web server is handling these 3 concurrent requests to the third-party APIs. To simulate this whole thing without external dependencies, I have everything running on my laptop. I have Tornado server or other framework server too, and I have a dummy local server that just waits for a fixed timeout of 10 milliseconds on every request and returns a dummy hello world greeting. And you can see it over here. So this is what my dummy local server does. Now we can test how fast can IPython notebook fetch this dummy server response directly, so that we have something to compare to. So it's 16 milliseconds. From these 16 milliseconds, 10 milliseconds is our fixed delay that we have on purpose, and 6 milliseconds for fetching overhead. So first example, we have just a blocking server. Just a blocking Tornado server that is using HTTP client, not async HTTP client. Therefore, it does not return futures. It blocks and it waits for result. In this list comprehension, I have 3 URLs, so 3 dummy URLs that I want to fetch. I'm calling fetch on each of them, and then I'm just looping over responses and writing it back to the user. This is how it will work. So we requested 3 times, same URL. We have the response. Let's see how fast does it go. OK, so this is 54 milliseconds altogether. Obviously, we just multiply this 16 by 3 because it's a blocking server. So it did it sequentially. Now let's see how the same thing, but just using the async HTTP client work. Basically, what do we need to do to convert blocking code to non-blocking code? We need to change the HTTP client into async HTTP client, so add this thing. Then we need to mark it as a coroutine in order to let Tornado or other framework in async.io, it would be also a coroutine decorator. We let it know that this thing that is beneath will yield us back the future, so that Tornado knows to process it accordingly. So we are calling this thing. We have the same response, and this should be 3 times faster. It's not, because of the overhead, of course. This whole thing, IO loop and stuff, has own overhead, but it's 22 milliseconds. So comparing to 54, it's 2.5 times less, more or less. And comparing to the requesting dummy URL directly, 16 versus 22, we have again about 5 milliseconds of the overhead of Tornado. Now the fun part comes. Node.js. So this is also a synchronous web framework, and probably everyone has already seen on the internet some article like, hey, my Node.js on the EC2 micro instance is handling, I don't know, 10, 100,000 of connections simultaneously. Yes, this is true. This does work, especially in the case of WebSockets. It is a perfect case for a synchronous framework to be used, because for WebSockets, we have many connections, but all of them are mostly idling. So we are wasting our CPU if we have resources dedicated to each of these connections. We want to use our resources efficiently. Therefore, at one point of time, we can have just one client getting real work done on the back end. Others can just wait, because WebSockets do not need everyone to do stuff at the same time. So this is how it works. I might, of course, have it not in the perfect way, as some JavaScript guru would advise me, but I did it on purpose because I try to avoid external dependencies. Node.js has a lot of external libraries that would make it kind of look nicer, but this is just pure Node thingy. So what we do here? I created the option object that keeps reference to the local host dummy URL. I have the array that is waiting for responses, that will get the responses. Then I need to loop. I'm looping over API count, which is 3, just to have 3 requests. And I do http.get. So http is a library that is kind of the async HTTP client in Tornado. And then I need to, of course, define a callback, what to do after we fetch stuff. And I'm defining it in line in the best tradition of the JavaScript. Need to set encoding. I need to create the body chunks, because this function will be called not when the result is ready, but when the chunk arrives. So on the data, I'm creating another inline function that will push this chunk to the array of chunks. Then on the end event that will send us after all chunks are there, I need to glue it back together by using buffer concat. Then I push responses to the body object. And finally, when I see that, OK, so responses are 3, just as API counts that was 3, I can say, OK, everything is ready now. Then I create the response text, I set headers, and that's it. I end the request. At the end, we have the same thing, and let's see how fast this works. We can remind what was in Tornado meanwhile, so it was 22 milliseconds for Tornado, and it's 18 for Node.js. Bravo, Node.js. Well done. We have 3 milliseconds faster, but maybe 4 hours more of our developer work. Let's have another example. Scala. Wonderful, performant language. I guys just don't have time to go through all of this mess. Believe me, you don't want to read it. I, of course, realize that the people who are experts in Scala do this pretty fast. In fact, I was not the guy who wrote this, because on every conference when I'm showing some Tornado examples, I ask someone who knows some other asynchronous framework to give me the example so that I can add it into my comparison. But the funny thing is that this thing is damn performant. Let's see how in practice does it work. 22 of Tornado, 18, 19, slightly more than Node, OK. But of course, this is not a very fair comparison, because I have a fixed number of backend APIs, which is 3. So I fetch 3 APIs. What if we have 10? What if we have 20? We don't need to speculate. I wrote a little benchmark that will answer us this question. So here, I have Tornado, I have Node.js, and I have Finagle. And I'm going to increase the number of concurrent requests from 1 to 20. Then I'm going to plot a graph that will show us how do these different frameworks behave on the increasing load, so on the increasing of the concurrent requests. And now it's ready. So here you see, Tornado was losing at the beginning, but it is quite stable at least. We see the total opposite question with Node.js, because somehow at 5 requests, it just blocks and jumps up. And in case of Scala and Finagle, it's perfect. OK, I have nothing to add here. Bravo to Scala. Tornado also did a good job. And I have a feeling that I might just have not a perfect configuration for Node, because we obviously see this pattern of jumping on every 5 parallel requests added. So I think that, yeah, we can stop at this point. Let me then jump back to my slides.